In this next series of videos, we'll get some more practice applying the divide and conquer algorithm design paradigm to various problems. This will also give us a glimpse of the kinds of application domains to which it's been successfully applied. We're going to start by extending the merge sort algorithm to solve a problem involving counting the number of inversions of an array. Before we tackle the specific problem of counting the number of inversions in an array, let me say a few words about the divide and conquer paradigm in general. So again, you've already seen the totally canonical example of divide and conquer, namely merge sort. So the following three conceptual steps will be familiar to you. The first step, no prizes for guessing, is you divide the problem into smaller subproblems. Sometimes this division happens only in your mind. It's really more of a conceptual step than part of your code. Sometimes you really do copy over parts of the input into, say, new arrays to pass on to your recursive calls. The second step, again, no prizes here, is you conquer the subproblems just using recursion. So for example, in merge sort, you conceptually divide the array into two different pieces, and then you recursively conquer or sort to the first half of the array, and you do the same thing with the second half of the array. Now, of course, it's not quite as easy as just doing these two steps, dividing the problem and then solving the subproblems recursively. Usually you have some extra cleanup work after the recursive calls end to stitch together the solutions to the subproblems into one for the big problem, the problem that you actually care about. Recall, for example, in merge sort, after our recursive calls, the left half of the array was sorted, the right half of the array was sorted, but we still had to stitch those together and merge into a sorted version of the entire array. So the third step is to combine the solutions to the subproblems into one of the original problem. Generally, the largest amount of ingenuity happens in the third step. How do you actually quickly combine solutions to subproblems into one to the original problem? Sometimes you also get some cleverness in the first step with division. Sometimes it's as simple as just splitting an array in two, but there are cases where the division step also has some ingenuity. Now let's move on to the specific problem of counting inversions and see how to apply this divide and conquer paradigm. So let me begin by defining the problem formally. We're given as input an array A of length n, and you could define the problem so that the array A contains any old distinct numbers, but let's just keep things simple and assume that it contains the numbers 1 through n, the integers in that range in some order. That captures the essence of the problem. And the goal is to compute the number of inversions of this array. So what's an inversion, you may ask? Well, inversion is just a pair of array indices I and j with I smaller than j, so that the earlier array entry, the ith entry, is bigger than the later one, than the jth one. So one thing that should be evident is that if the array contains these numbers in sorted order, if the array is simply 1, 2, 3, 4, all the way up to n, then the number of inversions is 0. The converse you might also want to think through: if the array has any other ordering of the numbers between 1 and n other than the sorted one, then it's going to have a non-zero number of inversions. Let's look at another example. So suppose we have an array of 6 entries, so the numbers 1 through 6 in the following order: 1, 3, 5, followed by 2, 4, 6. So how many inversions does this array have? So again, what we need to look for are pairs of array entries so that the earlier or left entry is bigger than the later or right entry. So one example which we see right here would be 5 and 2. Those are right next to each other and out of order. The earlier entry is bigger than the other one. But there's others. There's 3 and 2, for example. Those are out of order. And 5 and 4 are also out of order. And I'll leave it to you to check that those are the only 3 pairs that are out of order. So summarizing, the inversions in this array of length 6 are 3, 2, 5, 2, and 5, 4, corresponding to the array entries 2, 4, 3, 4, and 3, 5. Pictorially, we can think of it thusly. We can first write down the numbers in order, 1 up to 6, and then we can write down the numbers again, but ordered in the way that they're given in the input array. So 1, 3, 5, 2, 4, 6. And then we can connect the dots, meaning we connect 1 to 1, we connect 2 to 2, and so on. It turns out, and I'll leave it for you to think this through, that the number of crossing pairs of line segments precisely correspond to the number of inversions. So we see that there are 1, 2, 3 crossing line segments, and these are exactly in correspondence with the 3 inversions we found earlier: 5 and 2, 3 and 2, and 5 and 4. Now, why might you want to solve this problem, you might ask? Well, there's a few reasons it comes up, but one would be to have a numerical similarity measure that quantifies how close two different ranked lists are to each other. So for example, suppose I took you and a friend and I identified 10 movies that both of you had seen. And I asked each of you to rank these movies from your most favorite to your least favorite. Now I can form an array and compute inversions, and it quantifies in some sense how dissimilar your two rankings are to each other. So in more detail, in the first entry of this array, I would put down the ranking that your friend gave to your favorite movie. So if you had your favorite movie, Star Wars or whatever, and your friend only thought it was the 5th best out of the 10, then I would write down a 5 in the first entry of this array. Similarly, I would take your second favorite movie, I would look at how your friend ranked that, I would put that in the second entry of the array, and so on, all the way up to the 10th entry of the array, where I would put your friend's ranking of your least favorite movie. Now, if you have exactly identical preferences, if you rank them exactly the same way, the number of inversions of this array would be 0. And in general, the more inversions this array has, it quantifies that your lists look more and more different from each other. Now, why might you want to do this? Why might you want to know whether two different people ranked things in a similar way, had similar preferences? Well, one reason would be in what's called collaborative filtering. So probably many of you have had the experience of going to a website, and if you've made a few purchases from this website, it starts recommending further purchases for you. So one way to solve that problem under the hood is to look at your purchases, look at what you seem to like, find other people who have similar preferences, a similar history, look at things that they've bought that you haven't, and then recommend new products to you based on what similar customers seem to have bought. So this problem captures some of the essence of identifying which customers or which people are similar based on data about what they prefer. So just to make sure we're all on the same page, let me pause for a brief quiz. We've already noticed that a given array will have 0 inversions if and only if it's in sorted order, or if it only contains the numbers 1 through n in order. So on the other side, what is the largest number of inversions an array could possibly have? Let's say just for an array of size 6, like the one in this example here. So the answer to this question is the first one, 15, or in general, in an n-element array, the largest number of inversions is n choose 2, also known as n times n minus 1 over 2. Which again, in the case of a 6-element array, is going to evaluate to 15. The reason is the worst case is when the array is in backwards order, reverse sorted order, and then every single pair of array indices is inverted, and so the number of indices ij with I less than j is precisely n choose 2. Let's now turn our attention to the problem of computing the number of inversions of an array as quickly as possible. So one option which is certainly available to us is the brute force algorithm. And by brute force, I just mean we could set up a double for loop, one which goes through I, one which goes through j bigger than I, and we just check each pair ij individually with I less than j, whether that particular pair of array entities, ai and aj, is inverted. And if it is, then we add it to a running count. And then we return the final count at the end of the double for loop. That's certainly correct. The only problem is, as we just observed, there's n choose 2, or a quadratic number of potential inversions, so this algorithm is always going to run in time quadratic in the array length. Now remember the mantra of any good algorithm designer. Can we do better? And the answer is yes, and the method will be using divide and conquer. The way in which we divide will be motivated directly by merge sort, where we recurse separately on the left and the right halves of the array. We're going to do the same thing here. To understand how much progress we can make purely using recursion, let's classify the inversions of array into one of 3 types. So suppose we have an inversion of an array I comma j. And remember, in an inversion you always have I less than j. We're going to call it a left inversion if both of the array indices are at most n over 2, where n is the array length. We're going to call it a right inversion if they're both strictly greater than n over 2. And we're going to call it a split inversion if the smaller index is at most n over 2 and the larger index is bigger than n over 2. We can discuss the progress made by recursion in these terms. When we recurse on the left half of an array, if we implement our algorithm correctly, we'll successfully be able to count all of the inversions located purely in that first half. Those are precisely the left inversions. Similarly, a second recursive call on just the right half of an array, the second half of an array, will successfully count all of the right inversions. There remains the question of how to count the split inversions, but we shouldn't be surprised there's some residual work left over even after the recursive calls do their job. That, of course, was the case in merge sort. Recursion magically took care of sorting the left half of the array, sorting the right half of the array, but there was still, after their return, the matter of merging those 2 sorted lists into one. And here again, after the recursion, there's going to be the matter of cleaning up and counting the number of split inversions. So for example, if you go back to the 6-element array we worked through before, 1, 3, 5, 2, 4, 6, you'll notice that there, in fact, all of the inversions are split. So the recursive calls will both come back counting 0 inversions, and all of the work for that example will be done by the count split inversions subroutine. So let's summarize where things stand and give an underspecified high-level description of the algorithm as we envision it. There is a base case. I'll go ahead and write it down for completeness, which is if we're given a 1-element array, then there's certainly no inversion, so we can just immediately return the answer 0. For any bigger array, we're going to divide and conquer, so we'll count the left inversions with a recursive call, the right inversions with a recursive call, and then we'll have some currently unimplemented subroutine that counts the split inversions. Since every inversion is either left or right or split and can't be any more than one of those three, then having done these three things, we can simply return their sum. So that's our high-level attack on how we're going to count up the number of inversions. And of course, we need to specify how we're going to count the number of split inversions. And moreover, we like that subroutine to run quickly. An analogy to merge sort, where outside the recursive calls we did merely linear work, in the merge subroutine. Here we'd like to do only linear work in counting up the number of split inversions. If we succeed in this goal, if we produce a correct and linear time implementation to count up the number of split inversions, then this entire recursive algorithm will run in big O of n log n time. The reason the overall algorithm will run in O of n log n time is exactly the same reason that merge sort ran in n log n time. There's 2 recursive calls, each on a problem of half the size, and outside of the recursive calls we would be doing linear work. So you could copy down exactly the same recursion tree argument we used for merge sort. It would apply equally well here. Alternatively, very soon we will cover the master method, and as one very special case, it will prove that this algorithm, if we can implement it thusly, will run in O of n log n time. Now, one thing to realize is this is a fairly ambitious goal, to count up the number of split inversions in linear time. It's not that there can't be too many split inversions. There can actually be a lot of them. If you have an array where the first half of the array contains the numbers n over 2 plus 1 up to n, whereas the second part of the array contains the numbers 1 up to n over 2, that has a quadratic number of inversions, all of which are split. So what we're attempting to do here is count up a quadratic number of things using only linear time. Can it really be done? Yes, it can, as we'll see in the next video. So far, we've developed a divide and conquer approach to counting the number of inversions of an array. So we're going to split the array in 2 parts, recursively count inversions on the left, on the right. We've identified the key challenge as counting the number of split inversions quickly, where a split inversion means that the earlier index is on the left half of the array, the second index is on the right half of the array. These are precisely inversions that are going to be missed by both of our recursive calls. And the crux of the problem is that there might be as many as quadratic split inversions, yet somehow to get the runtime we want, we need to do it in linear time. So here's the really nice idea which is going to let us do that. The idea is to piggyback on merge sort. By which I mean we're actually going to demand a bit more of our recursive calls to make the job of counting the number of split recursions easier. This is analogous to when you're doing a proof by induction. Sometimes by making the inductive hypothesis stronger, that's what lets you push through the inductive proof. So we're going to ask our recursive calls to not only count inversions in the array that they're passed, but also along the way to sort the array. And hey, why not? We know sorting is fast. Merge sort will do it in n log n time, which is the runtime we're shooting for. So why not just throw that in? Maybe it'll help us in the combined step, and as we'll see, it will. So what is this bias? Why should we demand more of our recursive calls? Well, as we'll see in a couple slides, the merge subroutine almost seems designed just to count the number of split inversions. As we'll see, as you merge 2 sorted subarrays, you will naturally uncover all of the split inversions. So let me just be a little bit more clear about how our previous high-level algorithm is going to now be souped up so that the recursive calls sort as well. So here's the high-level algorithm we proposed before, where we just recursively count inversions on the left side, on the right side, and then we have some currently unimplemented subroutine count split inv, which is responsible for counting the number of split inversions. So we're just going to augment this as follows. So instead of being called count, now we're going to call it sort and count. So that's going to be the name of our algorithm. The recursive calls again just invoke sort and count. And so now we know each of those will not only count the number of inversions in the subarray, but also return a sorted version. So out from the first one, we're going to get array B back, which is the sorted version of the array that we passed it. and we'll get a sorted array C back from the second recursive call, the sorted version of the array that we passed it. And now the count split inversions, now in addition to counting split inversions, it's responsible for merging the two sorted subarrays B and C. So count split if will be responsible for outputting an array D, which is a sorted version of the original input array A. And so I should also rename our unimplemented subroutine to reflect its now more ambitious agenda. So we'll call this merge and count split inv. Now, we shouldn't be intimidated by asking our combining subroutine to merge the two sorted subarrays B and C, because we've already seen we know how to do that in linear time. So the question is just piggybacking on that work, can we also count the number of split inversions in an additional linear time? We'll see that we can, although that's certainly not obvious. So you should again at this point have the question, why on earth are we doing this? Why are we just making ourselves do more work? And again, the hope is that the payoff is somehow counting split inversions becomes easier by asking our recursive calls to do this additional work of sorting. So to develop some intuition for why that's true, why merging naturally uncovers the number of split inversions, let's recall what the definition of just the original merge subroutine for merge sort was. So here's the same pseudocode we went through several videos ago. I have renamed the letters of the arrays to be consistent with the current notation. So we're given two sorted subarrays. These come back from recursive calls. I'm calling them B and C. They both have length n over 2. And we're responsible for producing the sorted combination of B and C. So that's an output array D of length n. And again, the idea is simple. You just take the two sorted subarrays B and C, and then you take the output array D, which you're responsible for populating, and using index k, you're going to traverse the output array D from left to right. That's what this outer for loop here does. And you're going to maintain pointers I and j to the sorted subarrays B and C respectively. And the only observation is that whatever the minimum element that you haven't copied over to D yet is, it's got to be either the leftmost element of B that you haven't seen yet or the leftmost element of C that you haven't seen yet. B and C, by virtue of being sorted, the minimum element remaining has to be the next one available to either B or C. So you just proceed in the obvious way. You compare the two candidates for the next one to copy over. You look at B of I, you look at C of j. Whichever one is smaller, you copy over. So the first part of the if statement is for when B contains the smaller one. The second part of the else statement is for when C contains the smaller one. Okay, so that's how merge works. You go down B and C in parallel, populating D in sorted order from left to right. Now, to get some feel for what on earth any of this has to do with the split inversions of an array, I want you to think about an input array A that has the following property. That has the property that there are no split inversions whatsoever. So every inversion in this input array A is going to be either a left inversion, so both indices are at most n over 2, or a right inversion, so both indices are strictly greater than n over 2. Now the question is, given such an array A, once you're merging at this step, what do the sorted subarrays B and C look like for an input array A that has no split inversions? The correct answer is the second one, that if you have an array with no split inversions, then everything in the first half is less than everything in the second half. Why? Well, consider the contrapositive. Suppose you had even one element in the first half which was bigger than any element in the second half. That pair of elements alone would constitute a split inversion. Okay, so if you have no split inversions, then everything on the left is smaller than everything in the right half of the array. Now, more to the point, think about the execution of the merge subroutine on an array with this property, on an input array A, where everything in the left half is less than everything in the right half. What is merge going to do? Right, so remember, it's always looking for whichever is smaller, the first element of remaining in B or the first element remaining in C, and that's what it copies over. Well, if everything in B is less than everything in C, everything in B is going to get copied over into the output array D before C ever gets touched. Okay, so merge has an unusually trivial execution on input arrays with no split inversions, with zero split inversions. First, it just goes through B and copies it over. Then it just concatenates C. Okay, there's no interleaving between the two. So no split inversions means nothing gets copied from C until it absolutely has to, until B is exhausted. So this suggests that, perhaps, copying elements over from the second subarray C has something to do with the number of split inversions in the original array. And that is in fact the case. So we're going to see a general pattern about copies from the second element C, second array C into the output array, exposing split inversions in the original input array A. So let's look at a more detailed example to see what that pattern is. So let's return to the example in the previous video, which is an array with 6 elements ordered 1, 3, 5, 2, 4, 6. So we do our recursive call, and in fact the left half of the array is sorted and the right half of the array is already sorted. So no sorting work is going to be done, and we're actually going to get 0 inversions for both our recursive calls. Remember, in this example it turns out all of the inversions are split inversions. So now let's trace through the merge subroutine invoked on these two sorted subarrays and try to spot a connection with the number of split inversions in the original 6-element array. So we initialize indices I and j to point to the first element of each of these subarrays. So this left one is B and this right one is C, and the output is D. Now the first thing we do is we copy the 1 over from B into the output array. So 1 goes there, and we advance this index over to the 3. And here nothing really interesting happens. There's no reason to count any split inversions, and indeed the number 1 is not involved in any split inversions because 1 is smaller than all of the other elements, and it's also in the first index. Things are much more interesting when we copy over the element 2 from the second array C. And notice at this point we have diverged from the trivial execution that we would see with an array with no split inversions. Now we're copying something over from C before we've exhausted copying B. So we're hoping this will expose some split inversions. So we copy over the 2 and we advance the second pointer J into C. And the thing to notice is this exposes 2 split inversions, the 2 split inversions that involve the element 2. And those inversions are 3, 2 and 5, 2. So why did this happen? Well, the reason we copied 2 over is because it's smaller than all the elements we haven't yet looked at in both B and C. So in particular, 2 is smaller than the remaining elements in B, the 3 and the 5, but also because B is the left array, the indices of the 3 and 5 have to be less than the index of this 2. So these are inversions. 2 is further to the right in the original input array, and yet it's smaller than these remaining elements in B. So there are 2 elements remaining in B, and those are the 2 split inversions that involve the element 2. So now let's go back to the merging subroutine. So what happens next? Well, next we make a copy from the first array, and we sort of realize that nothing really interesting happens when we copy from the first array, at least with respect to split inversions. Then we copy the 4 over, and yet again we discover a split inversion, the remaining one, which is 5, 4. Again, the reason is, given that 4 was copied over before what's left in B, it's got to be smaller than it, but by virtue of being in the rightmost array, it's also got to have a bigger index, so it's got to be a split inversion. And now the rest of the merge subroutine executes without any real incident. The 5 gets copied over, and we know copies from the left array are boring, and then we copy the 6 over, and copies from the right array are generally interesting, but not if the left array is empty. That doesn't involve any split inversions. And you will recall from the earlier video that these were the inversions in the original array, 3, 2, 5, 2, and 5, 4. We discovered them all in an automated method by just keeping an eye out when we copy from the right array C. So this is indeed a general principle, so let me state the general claim. So the claim is not just in this specific example, in this specific execution, but no matter what the input array is, no matter how many split inversions there might be, the split inversions that involve an element of the second half of the array are precisely those elements remaining in the first array when that element gets copied over to the output array. So this is exactly the pattern that we saw in the example. So on the right array, C, we had the elements 2, 4, and 6. Remember, every split inversion has to, by definition, involve one element from the first half and one element from the second half. So to count the split inversions, we can just group them according to which element of the second array that they involve. So out of the 2, 4, and 6, the 2 is involved in the split inversions 3, 2, and 5, 2. The 3 and the 5 were exactly the elements remaining in B when we copied over 2. The split inversions involving 4 is exactly the inversion 5, 4, and 5 is exactly the element that was remaining in B when we copied over the 4. There's no split inversions involving 6, and indeed the element B was empty when we copied the 6 over into the output array D. So what's the general argument? Well, it's quite simple. Let's just zoom in and fixate on a particular element X that belongs to that first half of the array, that's amongst the first half of the elements. And let's just examine which Y's, so which elements of the second array, the second half of the original input array, are involved in split inversions with X. So there are 2 cases, depending on whether X is copied over into the output array D before or after Y. Now, if X is copied to the output before Y, well then since the output's in sorted order, it means X has got to be less than Y, so there's not going to be any split inversion. On the other hand, if y is copied to the output d before x, then again, because we populate d left to right in sorted order, that's got to mean that y is less than x. Now x is still hanging out in the left array, so it has a less index than y. Y comes from the right array, so this is indeed a split inversion. So putting these two together, it says that the elements x of the array b that form split inversions with y are precisely those that are going to get copied to the output array after y. So those are exactly the number of elements remaining in B when Y gets copied over. So that proves the general claim. So this slide was really the key insight. Now that we understand exactly why counting split inversions is easy as we're merging together two sorted subarrays, it's a simple matter to just translate this into code and get a linear time implementation of a subroutine that both merges and counts the number of split inversions, which then in the overall recursive algorithm will have n log n running time just as in merge sort. So let's just spend a quick minute filling in those details. So I'm not going to write out the pseudocode, I'm just going to write out what you need to augment the merge pseudocode discussed a few slides ago by in order to count split inversions as you're doing the merging. And this will follow immediately from the previous claim, which indicated how split inversions relate to the number of elements remaining in the left array as you're doing the merge. So the idea is the natural one, as you're doing the merging, according to the previous pseudocode of the two sorted subarrays, you just keep a running total of the number of split inversions that you've encountered. Right, so you've got your sorted subarray B, you've got your sorted subarray C, you're merging these into an output array D, and as you traverse through D and K goes from 1 to N, you just start the count at 0 and you increment it by something each time you do a copy over from either B or C. So what's the increment? Well, what did we just see? We saw that copies involving B don't count. We're not going to look at split inversions when we copy over from B, only when we look at them from C, right? Every split inversion involves exactly one element from each of B and C, so we may as well count them via the elements in C. And how many split inversions are involved with a given element of C? Well, it's exactly how many elements of B remain when it gets copied over. So that tells us how to increment this running count. And it follows immediately from the claim on the previous slide that this implementation of this running total counts precisely the number of split inversions that the original input array A possesses. And recall that the left inversions are counted by the first recursive call, the right inversions are counted by the second recursive call. Every inversion is either left or right or split. It's exactly one of those three types. So with our three different subroutines, the two recursive ones and this one here, we successfully count up all of the inversions of the original input array. So that's the correctness of the algorithm. What's the running time? Well, recall in merge sort, we began by just analyzing the running time of merge, and then we discussed the running time of the entire merge sort algorithm. Let's do the same thing here briefly. So what's the running time of this subroutine for this merging and simultaneously counting the number of split inversions? Well, there's the work that we do in the merging, and we already know that that's linear. And then the only additional work here is incrementing this running count, and that's constant time for each element of D, right? Each time we do a copy over, we do a single addition to our running count. So constant time per element of D, or linear time overall. So I'm being a little sloppy here. It's sloppy in a very conventional way, but it is a little sloppy by writing O of n plus O of n equals O of n. Be careful when you make statements like that, right? So if you added O of n to itself n times, it would not be O of n. But if you add O of n to itself a constant number of times, it is still O of n. So you might, as an exercise, want to write out a formal version of what this means. Basically, there's some constant C1 so that the merge step takes at most C1 n steps. There's a constant C2 so that the rest of the work is at most C2 times n steps. So when we add them, we get its most quantity C1 plus C2 times n steps, which is still big O of n because C1 plus C2 is a constant. Okay, so linear work for merge, linear work for the running count, so that's linear work in the subroutine overall. And now by exactly the same argument we used in merge sort, because we have two recursive calls on half the size, and we do linear work outside of the recursive calls, the overall running time is O of n log n. So we've really just piggybacked on merge sort up to the constant factor a little bit to do the counting along the way, but the running time remains big O of n log n. In this video, we'll apply the divide and conquer algorithm design paradigm to the problem of multiplying matrices. This will culminate in the study of Strassens matrix multiplication algorithm. And this is a super cool algorithm for two reasons. First of all, Strassens' algorithm is completely non-trivial. It's totally non-obvious, very clever, not at all clear how Strassen ever came up with it. The second cool feature is it's for such a fundamental problem. So computers, as long as they've been in use, from the time they were invented up till today, a lot of their cycles is spent multiplying matrices because it just comes up all the time in important applications. So let me first just make sure we're all clear on what the problem is of multiplying two matrices. So we're going to be interested in three matrices, x, y, and z. I'm going to assume they all have the same dimensions, n by n. The ideas we'll talk about are also relevant for multiplying non-square matrices, but we're not going to discuss it in this video. The entries in these matrices, you could think of it as whatever you want. Maybe they're integers, maybe they're rationals, maybe they're from some finite field. It depends on the application, but the point is they're just entries that we can add and multiply. So how is it that you take two n by n matrices, x and y, and multiply them, producing a new n by n matrix, z? Well, recall that the ij entry of z, that means the entry in the ith row and the jth column, is simply the dot product of the ith row of x with the jth column of y. So if ij was this red square, this red entry over in the z matrix, that would be derived from the corresponding row of the x matrix and the corresponding column of the y matrix. And recall what I mean by dot product. That just means you take the products of the individual components and then add up the results. So ultimately, the zij entry boils down to a sum over n things, where each of the constituent products is just the xik entry, the ik entry of the matrix x with the kj entry of the matrix y, or here k is ranging from 1 to n. So that's how zij is defined for a given pair of indices I and j. One thing to note is that where we often use n to denote the input size, here we're using n to denote the dimension of each of these matrices. The input size is not n. The input size is quite a bit bigger than n. Specifically, each of these are n by n matrices and contains n squared entries. So since presumably we have to read the input, which has size n squared, and we have to produce the output, which also has size n squared, the best we could really hope for a matrix multiplication algorithm would be a running time of n squared. So the question is, how close can we get to it? Before we talk about algorithms for matrix multiplication, let me just make sure we're all crystal clear on exactly what the problem is. So let's just actually spell out what would be the result of multiplying two different 2 by 2 matrices. So we can parameterize two generic 2 by 2 matrices by just giving the first one entries A, B, C, and D, where these four entries could all be anything. And then we're multiplying by a second 2 by 2 matrix. Let's call this entries E, F, G, and H. Now, what's the result of multiplying these? Where again, it's going to be a 2 by 2 matrix where each entry is just the corresponding dot product of the relevant row of the first matrix and column of the second matrix. So to get the upper left entry, we take the dot product of the upper row of the first matrix and the first column of the left column of the second matrix. So that results in AE plus BG. To get the upper right entry, we take the dot product of the top row of the left matrix with the right column of the second matrix. So that gives us AF plus BH. And then filling in the other entries in the same way, we get CE plus DG and CF plus DH. Okay, so that's multiplying two matrices, and we've already discussed the definition in general. Now, suppose you had to write a program to actually compute the result of multiplying two n by n matrices. One natural way to do that would just be to return to the definition, and which defines each of the n squared entries in the Z matrix as a suitable sum of products of entries of the X and Y matrices. So in the next quiz, I'd like you to figure out exactly what would be the running time of that algorithm as a function of the matrix dimension n, where as usual we count the addition or multiplication of two individual entries as a constant time operation. So the correct response to this quiz is the third answer, that the running time of the straightforward iterative algorithm runs in cubic time relative to the matrix dimension n. To see this, just recall what the definition of the matrix multiplication was. The definition tells us that each entry Zij of the output matrix Z is defined as the sum from k equal 1 to n of xik times ykj. That is the dot product of the ith row of the X matrix and the jth column of the Y matrix. I'm certainly assuming that we have the matrices represented in a way that we can access a given entry in constant time. And under that assumption, remember each of these products only takes constant time. And so then to compute Zij, we just have to add up these n products. So that's going to be theta of n time to compute a given zij, and then there's an n squared entries that we have to compute. There's n choices for I, n choices for j, so that gives us n squared times n, or cubic running time overall for the natural algorithm, which is really just a triple for loop which computes each entry of the output array separately using the dot product. So the question, as always, for the keen algorithm designer is, can we do better? Can we beat n cubed time for multiplying two matrices? And we might be especially emboldened with the progress that we've already seen in terms of multiplying two integers. We applied the divide and conquer algorithm to the problem of multiplying two n-digit integers, and we had both a naive recursive algorithm and a seemingly better algorithm due to Gauss, which made only 3 recursive calls. Now, we haven't yet analyzed the running time of that algorithm, but as we'll see later, that does indeed beat the quadratic running time of the grade school algorithm. So it's very natural to ask, can we do exactly the same thing here? There's the obvious n-cubed algorithm, which follows straight from the definition. Perhaps analogous to Gauss, we can have some clever divide and conquer method which beats cubic time. So that's what we're going to explore next. Let's recall the divide and conquer paradigm. What does it mean to use it? Well, we first have to identify smaller subproblems. So if we want to multiply two n by n matrices, we have to identify multiplications of smaller matrices that we can solve recursively. Once we've figured out how we want to divide the given problem into smaller ones, then in the conquer step, we simply invoke our own algorithm recursively. That's going to recursively multiply the smaller matrices together. And then, in general, we'll have to combine the results of the recursive calls to get the solution for the original problem, in our case, to get the product of the original two matrices from the product of whatever submatrices we identify. So how would we apply the divide and conquer paradigm to matrices? So we're given two n by n matrices, and we have to somehow identify smaller pairs of square matrices that we can multiply recursively. So the idea, I think, is fairly natural. So we start with a big n by n matrix X. Right, so there's n rows and n columns, and we have to somehow divide it into smaller pieces. Now, the first thing you might think about is you put it into its left half and its right half, analogous to what we've been doing with arrays. But then we're going to break X into two matrices which are no longer square, which are n over 2 in one dimension and have length n in the other dimension. And we want to recursively call a subroutine that multiplies square matrices. So what seems like the clear thing to do is to divide X into quadrants. Okay, so we have 4 pieces of X. Each is going to be n over 2 by n over 2, corresponding to the different quarters of this matrix. So let's call these different quadrants, or blocks, in matrix terminology, A, B, C, and D. All of these are n over 2 by n over 2 matrices. As usual, for simplicity, I'm assuming that n is even, and as usual, it doesn't really matter. And we can do the same trick with Y. So we'll divide Y into quadrants, n over 2 by n over 2 matrices, which we'll call E, F, G, and H. So one thing that's cool about matrices is when you split them into blocks and you multiply them, the blocks just behave as if they were atomic elements. So what I mean by that is that the product of X and Y can be expressed in terms of its quadrants. And each of its 4 quadrants, each of its 4 corners, can be written as a suitable arithmetic expression of the quadrants of X and Y. So here's exactly what those formulas are. They're exactly analogous to when we just multiplied a pair of 2 by 2 matrices. So I'm not going to formally prove this fact. I'm sure many of you have seen it before, or familiar with it. And if you haven't, it's actually quite easy to prove. It's not obvious. You can't see it off the top of your head necessarily. But if you go back to the definition, it's quite easy to verify that indeed, when you multiply X and Y, you can express its quadrants into blocks in terms of the blocks of X and Y. So what we just did is completely analogous to when talking about integer multiplication, and we wanted to multiply 2 integers, little x and little y, and we broke them into pairs of n over 2 digits. And then we just took the expansion, and we observed how that expansion could be written in terms of products of n over 2 digit numbers. Same thing going on here, except with matrices. So now we're in business as far as a recursive approach. We want to multiply X and Y, they're n by n matrices, but we recognize we can express that product, X times Y, in terms of the products of n over 2 by n over 2 matrices, things we're able to multiply recursively, plus additions. And additions is clearly easy. To multiply 2 different matrices with, say, n squared entries each, it's going to be linear in the number of entries. So it's going to be n squared time to add 2 matrices that are n by n. So this immediately leads us to our first recursive algorithm. To describe it, let me quickly rewrite that expression we just saw on the previous slide. And now our first recursive algorithm is simply to evaluate all of these expressions in the obvious way. So specifically in step 1, we recursively compute all of the necessary products. And observe that there are 8 products that we have to compute, 8 products of n over 2 by n over 2 matrices. There are 4 entries in this expansion of x times y. Each of the blocks is the sum of 2 products, and none of the products reoccur. They're all distinct. So naively, if we want to evaluate this, we have to do 8 different products of n over 2 by n over 2 matrices. Once those recursive calls complete, then all we do is do the necessary 4 additions. As we discussed, that takes time proportional to the number of entries in the matrix, so this is going to take a quadratic time overall, quadratic in n, linear in the number of entries. Now, the question you should be asking is this a good algorithm? Was this good for anything, this recursive approach, splitting x and y into these blocks, expanding the product in terms of these blocks, then recursively computing each of the blocks? And I want to say it's totally not obvious. It is not clear what the running time of this recursive algorithm is. I'm going to go ahead and give you a spoiler, which is going to follow from the master method that we'll talk about in the next lecture. But it turns out with this kind of recursive algorithm, where you do 8 recursive calls, each on a problem with dimension half as much as what you started with, and then do quadratic time outside, the running time is going to be cubic. So exactly the same as with the straightforward iterative algorithm that follows from the definition. That was cubic, it turns out, and that was clearly cubic. This one, although it's not obvious, is cubic as well. So no better, no worse than the straightforward iterative algorithm. So in case you're feeling disappointed that we went through all this work and this sort of seemingly clever divide and conquer approach for matrix multiplication and came out at the end no better than the iterative algorithm, well, there's really no reason to despair. Because remember, back in integer multiplication, we had a straightforward recursive algorithm where we had to do 4 recursive calls, products of n over 2-digit numbers. But then we had Gauss's trick, which said, oh, if we only did more clever products and more clever additions and subtractions, then we can get away with only 3 recursive calls. And we'll see later that that is indeed a significant savings in the time needed for integer multiplication. And we've done nothing analogously clever to Gauss's trick for this matrix multiplication problem. All we did is the naive expansion in terms of submatrices and the naive evaluation of the resulting expressions. So the $64,000 question is then, can we do something clever to reduce the number of recursive calls from 8 down to something lower? And that is where Strassens' algorithm comes in. So at a high level, Strassens' algorithm has 2 steps, just like the first recursive algorithm that we discussed. It recursively computes some products of smaller matrices, n over 2, or roughly n over 2 by n over 2 matrices. But there's only going to be 7 of them. They will be much less straightforward. They will be much more cleverly chosen than in the first recursive algorithm. And step 2 then is to actually produce the product of x and y, produce each of those 4 blocks that we saw with suitable additions and subtractions of these 7 products. And again, these are much less straightforward than in the first recursive algorithm. And so while the additions and subtractions involved will be a little bit more numerous than they were in the naive recursive algorithm, it's only going to change the work in that part of the algorithm by a constant factor. So we'll still spend only theta of n squared work adding and subtracting things, and we get a huge win in decreasing the number of recursive calls from 8 to 7. Now, just in case you have the intuition that shaving off 1 of 8 recursive calls should only decrease the running time of an algorithm by 1/8, by 12.5%, in fact, it has a tremendously more amplified effect because we do 1 less recursive call over and over and over again as we keep recursing in the algorithm. So it makes a fundamental difference in the eventual running time of the algorithm, as we'll explore in detail in the next set of lectures when we discuss the master method. So again, a bit of a spoiler alert. What you're going to see in the next set of lectures is that indeed Strassens' algorithm does beat cubic time. It's better than n cubed time. You'll have to watch the next set of lectures if you want to know just what the running time is, but I'm going to tell you now that savings of the 8th recursive call is what changes the algorithm from cubic to subcubic. Now, 1969 was obviously quite a bit before my time, but by all accounts, from people I've talked to who were around then and from what the books say, Strassens' algorithm totally blew people's minds at the time. Everybody was assuming that there's no way you could do better than the iterative algorithm, the cubic algorithm. It just seemed that matrix multiplication intuitively fundamentally required all of the calculations that are spelled out in the definition. So Strassens' algorithm is an early glimpse of the magic and of the power of clever algorithm design. That if you really have a serious ingenuity, even for super fundamental problems, you can come up with fundamental savings over the more straightforward solutions. So those are the main points I wanted to talk about Strassens' algorithm, how you can beat cubic time by saving a recursive call with suitably chosen clever products and clever additions and subtractions. Maybe a few of you are wondering, what are these cleverly chosen products? Can you really do this? And I don't blame you. There's no reason to believe me just because I sort of spelled out this high-level idea. It's not obvious this should work. You might want to actually see the products. So for those of you like that, this last slide is for you. So here is Strassens' algorithm in its somewhat gory detail. So let me tell you what the 7 products are that we're going to form. I'm going to label them P1 through P7, and they're all going to be defined in terms of the blocks of the input matrices X and Y. So let me just remind you that we think of X in terms of its blocks, A, B, C, D, and we think of Y in terms of its blocks, E, F, G, H. And remember, A through H are all n over 2 by n over 2 submatrices. So here are the 7 products, P1 through P7. P1 is A times quantity F minus H. P2 is quantity A plus B times H. P3 is C plus D times E. P4 is D times G minus E. P5 is quantity A plus D times quantity E plus H. P6 is quantity B minus D times quantity G plus H. And finally, P7 is quantity A minus C, E plus F. So I hope you'll agree that these are indeed only 7 products, and we could compute these with 7 recursive calls. So we pre-process with a little bit of additions and subtractions. We have to compute F minus H, A plus B, C plus D, and so on. We compute all of these new matrices from the blocks, and we can then recursively, with 7 recursive calls, do these 7 products that operate on n over 2 by n over 2 matrices. Now, the question is, why is this useful? Why on earth would we want to know the values of these 7 products? So the amazing other part of the algorithm is that from just these 7 products, we can, using only addition and subtraction, recover all 4 of the blocks of a x times y. So x times y, you'll recall we expanded in terms of the blocks. So we previously computed this to be AE plus BG in the upper left corner, and then similarly expressions for the upper right, lower left, and lower right blocks. So this we already know. So the content of the claim is that these 4 blocks also arise from the 7 products in the following way. So the claim here is that these 2 different expressions for x times y are exactly the same, and they're the same block by block. So in other words, what the claim is that this crazy expression, P5 plus P4 minus P2 plus P6, where those are 4 of the products that we've listed above, that is precisely AE plus BG. Similarly, we're claiming that P1 plus P2 is exactly AF plus BH. That's actually easy to see. P3 plus P4 is CE plus DG. That's also easy to see. And then the other complicated one is that P1 plus P5 minus P3 minus P7 is exactly the same as CF plus DH. So all 4 of those hold. So let me, just so you believe me, because I don't know why you would believe me unless I actually showed you some of this derivation, let's just look at the proof of one of the cases of the upper left corner. So that is, let's just expand out this crazy expression, P5 plus P4 minus P2 plus P6. What do we get? Well, from P5 we get AE plus AH plus DE plus DH. Then we add P4, so that's going to give us plus DG minus DE. Then we subtract P2, so that gives us a minus AH minus BH. And then we add in P6. So that gives us a BG plus BH minus DG minus DH. Okay, so what happens next? Well, now we look for cancellations. So we cancel the AHs, we cancel the DEs, we cancel the DHs, we cancel the DGs, we cancel the BHs, and holy cow, what do we get? We get AE plus BG. That is, we get exactly what we were supposed to in the upper left block of x times y. So we just actually verified that this equation holds for the upper left block. It's quite easy to see that it holds for the upper right and lower left blocks, and a comparable calculation verifies it for the lower right blocks of the two. So summarizing, because this claim holds, because actually we can recover the 4 blocks of x times y from these 7 products, Strassens' algorithm works in the following way. You compute the 7 products P1 through P7 using 7 recursive calls. Then you just compute the 4 blocks using some extra additions and subtractions as shown in the claim. So 7 recursive calls on n over 2 by n over 2 matrices plus n squared work to do the necessary additions. And as you'll see in the master method lecture, that is actually sufficient for subcubic time. Now, I sympathize with you if you have the following question, which is, how on earth did Strassen come up with this? And indeed, this sort of illustrates the difference between checking somebody's proof and coming up with a proof. Given that I told you the magical 7 products and how you, from them, can recover the 4 desired blocks of x times y, it's really just mechanical to see that it works. It's a totally different story of how do you come up with P1 through P7 in the first place. So how did Strassen come up with them? Honestly, your guess is as good as mine. So in this video and the next, we're going to study a very cool divide and conquer algorithm for the closest pair problem. This is a problem where you're given endpoints in the plane and you want to figure out which pair of points are closest to each other. So this will be the first taste we get of an application in computational geometry, which is the part of algorithms which studies how to reason and manipulate geometric objects. So those algorithms are important in, among other areas, robotics, computer vision, and computer graphics. So this is relatively advanced material. It's a bit more difficult than the other applications of divide and conquer that we've seen. The algorithm's a little bit tricky, and it has a quite non-trivial proof of correctness. So just be ready for that, and also be warned that because it's more advanced, I'm going to talk about the material at a slightly faster pace than I do in most of the other videos. So let's begin now by defining the problem formally. So we're given as input endpoints in the plane, so each one just defined by its x-coordinate and its y-coordinate. And when we talk about the distance between 2 points in this problem, we're going to focus on Euclidean distance. So let me remind you what that is briefly, but we'll introduce some simple notation for that, which we'll use for the rest of the lecture. So we're just going to note the Euclidean distance between 2 points pi and pj by d of pi pj. So in terms of the x and y coordinates of these 2 points, we just look at the squared differences in each coordinate, sum them up, and take the square root. And now, as the name of the problem would suggest, the goal is to identify among all pairs of points that pair which has the smallest distance between them. Next, let's start getting a feel for the problem by making some preliminary observations. First, I want to make an assumption, purely for convenience, that there's no ties. So that is, I'm going to assume all endpoints have distinct x-coordinates, and also all endpoints have distinct y-coordinates. It's not difficult to extend the algorithm to accommodate ties. I'll leave it to you to think about how to do that. So next, let's draw some parallels with the problem of counting inversions, which was an earlier application of divide and conquer that we saw. The first parallel I want to point out is that if we're comfortable with a quadratic time algorithm, then this is not a hard problem. We can simply solve this by brute force search. And again, by brute force search, I just mean we set up a double for loop, which iterates over all distinct pairs of points. We compute the distance for each such pair, and we remember the smallest. That's clearly a correct algorithm. It has to iterate over a quadratic number of pairs, so its running time is going to be theta of n squared. And as always, the question is, can we apply some algorithmic ingenuity to do better? Can we have a better algorithm than this naive one which iterates over all pairs of points? You might have an initial instinct that because the problem asks about a quadratic number of different objects, perhaps we fundamentally need to do quadratic work. But again, recall back in counting inversions, using divide and conquer, we were able to get an n log n algorithm, despite the fact that there might be as many as a quadratic number of inversions in an array. So the question is, can we do something similar here for the closest pair problem? Now, one of the keys to getting an n log n time algorithm for counting inversions was to leverage a sorting subroutine. Recall that we piggybacked on merge sort to count the number of inversions in n log n time. So the question is, here with the closest pair problem, perhaps sorting again can be useful in some way to beat the quadratic barrier. So to develop some evidence that sorting will indeed help us compute the closest pair of points and better than quadratic time, let's look at a special case of the problem, really an easier version of the problem, which is when the points are just in one dimension, so on the line rather than in two dimensions in the plane. So in the 1D version, all of the points just lie on a line like this one, and we're given the points in some arbitrary order, not necessarily in sorted order. So a way to solve the closest pair problem in one dimension is to simply sort the points, and then of course the closest pair better be adjacent in this ordering, so you just iterate through the n-1 consecutive pairs and see which one is closest to each other. So more formally, here's how you solve the one-dimensional version of the problem. You sort the points according to their only coordinate, because again remember this is one dimension. So as we've seen using merge sort, we can sort the points in n log n time. And then we just do a scan through the points, so this takes linear time, and for each consecutive pair we compute their distance and we remember the smallest of those consecutive pairs and we return that. That's got to be the closest pair. So in this picture on the right, I'm just going to circle here in green the closest pair of points. So this is something we discover by sorting and then doing a linear scan. Now, needless to say, this isn't directly useful. This is not the problem I started out with. We wanted to find the closest pair among points in the plane, not points in the line. But I want to point out that this, even in the line, there are a quadratic number of different pairs. So brute force search is still a quadratic time algorithm, even in the 1D case. So at least with one dimension, we can use sorting, piggyback on it, to beat the naive brute force search bound and solve the problem in n log n time. So our goal for this lecture is going to be to devise an equally good algorithm for the two-dimensional case. So we want to solve closest pair of points in the plane, again in n log n time. So we will succeed in this goal. I'm going to show you an n log n time algorithm for 2D closest pair. It's going to take us a couple steps. So let me begin with the high-level approach. All right, so the first idea to try is just to copy what worked for us in the one-dimensional case. So in the one-dimensional case, we first sorted the points by their coordinate, and that was really useful. Now in the 2D case, points have two coordinates, x coordinates and y coordinates, so there's two ways to sort them. So let's just sort them both ways. That is, the first step of our algorithm, which you should really think of as a pre-processing step. We're going to take the input points, we invoke merge sort once to sort them according to x coordinate, that's one copy of the points, and then we make a second copy of the points where they're sorted by y coordinate. So we're going to call those copies of points px, that's an array of the points sorted by x coordinate, and py for them sorted by y coordinate. Now we know merge sort takes n log n time, so this pre-processing step only takes O of n log n time. And again, given that we're shooting for an algorithm with running time big O of n log n, why not sort the points? We don't even know how we're going to use this fact right now, but it's sort of harmless. It's not going to affect our goal of getting a big of O of n log n time algorithm. And indeed, this illustrates a broader point, which is one of the themes of this course. So recall, I hope one of the things you take away from this course is a sense for what are the four free primitives. What are manipulations or operations you can do on data, which basically are costless, meaning that if your data set fits in the main memory of your computer, you can basically invoke the primitive and it's just going to run blazingly fast. And you can just do it even if you don't know why. And again, sorting is the canonical for free primitive, although we'll see some more later in the course. And so here we're using exactly that principle. So we don't even understand why yet we might want the points to be sorted. It just seems like it's probably going to be useful, motivated by the 1D case. So let's go ahead and make sorted copies of the points by x and y coordinate up front. So reasoning by analogy with the 1D case suggests that sorting the points might be useful, but we can't carry this analogy too far. So in particular, we're not going to be able to get away with just a simple linear scan through these arrays to identify the closest pair of points. So to see that, consider the following example. So we're going to look at a point set which has 6 points. There's going to be 2 points, which I'll put in blue, which are very close in x coordinate, but very far away in y coordinate. And then there's going to be another pair of points, which I'll do in green, which are very close in y coordinate, but very far away in x coordinate. And then there's going to be a red pair of points, which are not too far away in either the x coordinate or the y coordinate. So in this set of 6 points, the closest pair is the pair of red points, but they're not even going to show up consecutively in either of the two arrays, right? So in the array that's sorted by x coordinate, this blue point here is going to be wedged in between the two red points. They won't be consecutive. And similarly in py, which is sorted by y coordinate, this green point is going to be wedged between the two red points. So you won't even notice these red points if you just do a linear scan through px and py and look at the consecutive pairs of points. So following our preprocessing step where we just invoke merge sort twice, we're going to do a quite non-trivial divide and conquer algorithm to compute the closest pair. So really in this algorithm, we're applying the divide and conquer algorithm twice. First, internal to the sorting subroutine, assuming that we use the merge sort algorithm to sort, divide and conquer is being used there to get an n log n running time in this preprocessing step, and then we're going to use it again on the sorted arrays in a new way, and that's what I'm going to tell you about next. So let's just briefly review the divide and conquer algorithm design paradigm before we apply it to the closest pair problem. So as usual, the first step is to figure out a way to divide your problem into smaller subproblems. Sometimes this has a reasonable amount of ingenuity, but it's not going to here in the closest pair problem. We're going to proceed exactly as we did in the merge sort and counting inversions problems, where we took the array and broke it into its left and right half. So here we're going to take the input point set and again just recurse on the left half of the points and recurse on the right half of the points. Where here by left and right I mean with respect to the points x coordinates. There's pretty much never any ingenuity in the conquer step. That just means you take the subproblems you identified in the first step and you solve them recursively. That's what we'll do here. We'll recursively compute the closest pair in the left half of the points and the closest pair in the right half of the points. So where all the creativity in divide and conquer algorithms lie is in the combined step. Given solutions to your subproblems, how do you somehow recover a solution to the original problem, the one that you actually care about? So for closest pair, the question is going to be, given that you've computed the closest pair on the left half of the points, the closest pair on the right half of the points, how do you then quickly recover the closest pair from the whole point set? That's a tricky problem. That's what we're going to spend most of our time on. So let's make this divide and conquer approach for closest pair a little bit more precise. So let's now actually start spelling out our closest pair algorithm. The input we're given, this follows the preprocessing step. So recall that we invoke merge sort twice. We get our two sorted copies of the point set px sorted by x coordinate and py sorted by y coordinate. So the first step then is the division step. So given that we have a copy of the points px sorted by x coordinate, it's easy to identify the leftmost half of the points, those with those n over 2 smallest x coordinates, and then the right half, those with the n over 2 largest x coordinates. We're going to call those q and r respectively. One thing I'm skipping over is the base case. I'm not going to bother writing that down. So base case omitted, but it's what you would think it would be. So basically once you have a small number of points, say 2 points or 3 points, then you can just solve the problem in constant time by brute force search. You just look at all the pairs and you return the closest pair. So think of there being at least 4 points in the input. Now in order to recurse, to call closest pair again on the left and right halves, we need sorted versions of q and r, both by x coordinate and by y coordinate. So we're just going to form those by doing suitable linear scans through px and py. And so one thing I encourage you to think through carefully, or maybe even code up after the video, is how would you form qx, qy, rx, and ry, given that you already have px and py. And if you think about it, because px and py are already sorted, just producing these sorted sublists takes linear time. It's in some sense the opposite of the merge subroutine we used in merge sort. Here we're sort of splitting rather than merging. But again, this can be done in linear time. That's something you should think through carefully later. So that's the division step. Now we just conquer, meaning we recursively call closest pair on each of the two subproblems. So when we invoke closest pair on the left half of the points on Q, we're going to get back what are indeed the closest pair of points amongst those in Q. So we're going to call those P1 and PQ. So among all pairs of points that both lie in Q, P1 and Q1 minimize the distance between them. Similarly, we're going to call P2, Q2 the results of the second recursive call. That is, P2 and Q2 are amongst all pairs of points that both lie in R, the pair that has the minimum Euclidean distance. Now conceptually there's two cases. There's a lucky case and there's an unlucky case. In the original point set P, if we're lucky, the closest pair of points in all of P, actually both of them lie in Q or both of them lie in R. In this lucky case, we'd already be done. If the closest pair in the entire point set, they happen to both lie in Q, then this first recursive call is going to recover them, and we just have them in our hands, P1, Q1. Similarly, if both of the closest pair of points in all of P lies on the right side, in R, then they get handed to us on a silver platter by the second recursive call that just operates on R. So in the unlucky case, the closest pair of points in P happens to be split. That is, one of the points lies in the left half in Q, and the other point lies in the right half in R. Notice, if the closest pair of points in all of P is split, is half in Q and half in R, neither recursive call is going to find it. Okay, the pair of points is not passed to either of the two recursive calls, so there's no way it's going to be returned to us. Okay, so we have not identified the closest pair after these two recursive calls if the closest pair happens to be split. This is exactly analogous to what happened when we were counting inversions. The recursive call in the left half of the array counted the left inversions, the recursive call in the right half of the array counted the right inversions, but we still had to count the split inversions. So in this closest pair algorithm, we still need a special purpose subroutine that computes the closest pair for the case in which it is split, in which there's one point in Q and one point in R. So just like in counting inversions, I'm going to write down that subroutine. I'm going to leave it unimplemented for now. We'll figure out how to implement it quickly in the rest of the lecture. Now, if we have a correct implementation of closest split pair, so that takes as input the original point set sorted by x and y coordinate and returns the smallest pair that's split, where one point's in Q and one point's in R, then we're done. So then the closest pair has to either be on the left or on the right, or it has to be split. Steps 2 through 4 compute the closest pair in each of those categories, so those are the only possible candidates for the closest pair, and we just return the best of them. So that's an argument for why, if we have a correct implementation of the closest split pair subroutine, then that implies a correct implementation of closest pair. Now, what about the running time? So the running time of the closest pair algorithm is going to be in part determined by the running time of closest split pair. So in the next quiz, I want you to think about what kind of running time we should be shooting for with a closest split pair subroutine. So the correct response to this quiz is the second one. And the reasoning is just by analogy with our previous algorithms for merge sort and for counting inversions. So what is all of the work that we would do in this algorithm? Well, we do have this pre-processing step we call merge sort twice. We know that's n log n, so we're not going to have a running time better than n log n because we sort at the beginning. And then we have a recursive algorithm with the following flavor. It makes 2 recursive calls. Each recursive call is on a problem of exactly half the size with half the points of the original one. And outside of the recursive calls, by assumption, in the problem, we do a linear amount of work in computing the closest split pair. So the exact same recursion tree, which proves an n log n bound for merge sort, proves an n log n bound for how much work we do after the pre-processing step. So that gives us an overall running time bound of n log n. And remember, that's what we were shooting for. We were working n log n already to solve the one-dimensional version of closest pair, and the goal of these lectures is to have an n log n algorithm for the 2D version. So this would be great. So in other words, the goal should be to have a correct linear time implementation of the closest split pair subroutine. If we can do that, we're home free. We get the desired n log n algorithm. Now, I'm going to proceed in a little bit to show you how to implement closest split pair, but before I do that, I want to point out one subtle but key idea, which is going to allow us to get this linear time correct implementation. So let me just put that on this slide. So the key idea is that we don't actually need a full-blown correct implementation of the closest split pair subroutine. So I'm not actually going to show you a linear time subroutine that always correctly computes the closest split pair of a point set. The reason I'm not going to do that is that's actually a strictly harder problem than what we need to have a correct recursive algorithm. We do not actually need a subroutine that, for every point set, always correctly computes the closest split pair of points. Remember, there's a lucky case and there's an unlucky case. The lucky case is where the closest pair in the whole point set P happens to lie entirely in the left half of the points Q or in the right half of the points R. In that lucky case, one of our recursive calls will identify this closest pair and hand it over to us on a silver platter. We could care less about the split pairs in that case. We get the right answer without even looking at the split pairs. Now there's this unlucky case where the split pair happens to be the closest pair of points. That is when we need this linear time subroutine, and only then, only in the unlucky case where the closest pair of points happens to be split. Now that's in some sense a fairly trivial observation, but there's a lot of ingenuity here in figuring out how to use that observation, the fact that we only need to solve a strictly easier problem, and that will enable the linear time implementation that I'm going to show you next. So now let's rewrite the high-level recursive algorithm slightly to make use of this observation that the closest split pair subroutine only has to operate correctly in the regime of the unlucky case, when in fact the closest split pair is closer than the result of either recursive call. So I've erased the previous steps 4 and 5, but we're going to rewrite them in a second. So before we invoke closest split pair, what we're going to do is we're going to see how well did our recursive calls do. That is, we're going to define a parameter little delta, which is going to be the closest pair that we found, or the distance of the closest pair we found by either recursive call. So the minimum of the distance between P1 and Q1, the closest pair that lies entirely on the left, and P2, Q2, the closest pair that lies entirely on the right. Now we're going to pass this delta information as a parameter into our closest split pair subroutine. We're going to have to see why on earth that would be useful. I still owe you that information, but for now we're just going to pass delta as a parameter for use in closest split pair. And then as before, we just do a comparison between the 3 candidate closest pairs and return the best of the trio. And so just so we're all clear on where things stand, so what remains is to describe the implementation of closest split pair. And before I describe it, let me just be crystal clear on what it is that we're going to demand of the subroutine. What do we need to have a correct and O of n log n time closest pair algorithm? Well, as you saw in the quiz, we want the running time to be O of n always. And for correctness, what do we need? Again, we don't need it to always compute the closest split pair, but we need it to compute the closest split pair in the event that there is a split pair of distance strictly less than delta, strictly better than the outcome of either recursive call. So now that we're clear on what we want, let's go ahead and go through the pseudocode for this closest split pair subroutine. And I'm going to tell you up front, it's going to be fairly straightforward to figure out that the subroutine runs in linear time, O of n time. The correctness requirement of closest split pair will be highly non-obvious. In fact, after I show you the pseudocode, you're not going to believe me. You're going to look at the pseudocode and you're going to be like, what are you talking about? But in the second video on the closest pair lecture, we will in fact show that this is a correct subroutine. So how does it work? Well, let's look at a point set. So the first thing we're going to do is a filtering step. We're going to prune a bunch of the points away and sort of zoom in on a subset of the points. And the subset of the points we're going to look at is those that lie in a vertical strip, which is roughly centered in the middle of the point set. So here's what I mean. By centered, we're going to look at the middle x-coordinate. So let x bar be the biggest x-coordinate in the left half. So that is, in the sorted version of the points by x-coordinate, we look at the n over 2th smallest x-coordinate. So in this example where we have 6 points, all this means is we imagine drawing a line between the third point. So that's going to be x bar, the x-coordinate of the third point from the left. Now, since we're passed as input a copy of the points sorted by x-coordinate, we can figure out what x bar is in constant time, just by accessing the relevant entry of the array px. Now, the way we're going to use this parameter delta that we're passed, so remember what delta is. So before we invoke the closest split pair subroutine in the recursive algorithm, we make our 2 recursive calls. We find the closest pair on the left, the closest pair on the right, and delta is whatever the smaller of those 2 distances are. So delta is the parameter that controls whether or not we actually care about the closest split pair or not. We care if and only if there is a split pair at distance less than delta. So how do we use delta? Well, that's going to determine the width of our strip. So the strip's going to have width 2 delta, and it's going to be centered around x. And the first thing we're going to do is we're going to ignore forevermore points which do not lie in this vertical strip. So the rest of the algorithm will operate only on the subset of P, the subset of the points that lie in this strip. And we're going to keep track of them sorted by y-coordinate. So the formal way to say that they lie in this strip is that they have x-coordinate in the interval with lower endpoint x bar minus delta and upper endpoint x bar plus delta. Now, how long does it take to construct this set sy sorted by y-coordinate? Well, fortunately, we've been passed as input a sorted version of the points py. So to extract sy from py, all we need to do is a simple linear scan through py, checking for each point where its x-coordinate is. So this can be done in linear time. Now, I haven't yet shown you why it's useful to have this sorted set sy, but if you take it on faith that it's useful to have the points in this vertical strip sorted by y-coordinate, you now see why it was useful that we did this merge sort all the way at the beginning of the algorithm, before we even underwent any recursion. Remember, what is our running time goal for closest split pair? We want this to run in linear time. That means we cannot sort inside the closest split pair subroutine. That would take too long. We want this to be linear time. Fortunately, since we sorted once and for all at the beginning of the closest pair algorithm, extracting sorted sublists from those sorted lists of points can be done in linear time, which is within our goals here. Now it's the rest of the subroutine where you're never going to believe me that it does anything useful. So I claim that essentially with a linear scan through SY, we're going to be able to identify the closest split pair of points in the interesting, unlucky case where there is such a split pair with distance less than delta. So here's what I mean by that linear scan through SY. So as we do the scan, we're going to keep track of the closest pair of points of a particular type that we've seen so far. So let me introduce some variables to keep track of the best candidate we've seen so far. So there's going to be a variable best, which will initialize to be delta. Remember, we're uninterested in split pairs unless they have distance strictly less than delta. And then we're going to keep track of the points themselves, so we'll initialize the best pair to be null. Now here's the linear scan. So we go through the points of SY in order of y coordinate. Okay, well, not quite all the points of SY. We stop at the 8th to last point, and you'll see why in a second. And then for each position I of the array SY, we investigate the 7 subsequent points of this same array SY. So for j going from 1 to 7, we look at the ith and I plus jth entry of SY. So if SY looks something like this array here, at any given point in this double for loop, we're generally looking at an index I, a point in this ith entry of the array, and then some really quite nearby point in the array I plus j, because j here is going to be at most 7. Okay, so we're constantly looking at pairs in this array, but we're not looking at all pairs at all. We're only looking at pairs that are very close to each other within 7 positions of each other. And what do we do for each choice of I and j? Well, we just look at those points, we compute the distance, we see if it's better than all of the pairs of points of this form that we've looked at in the past, and if it is better, then we remember it. So we just remember the best, i.e. closest pair of points of this particular type for choices of I and j of this form. So in more detail, if the distance between the current pair of points P and Q is better than the best we've seen so far, we reset the best pair of points to be equal to P and Q, and we reset the best distance, the closest distance seen so far, to be the distance between P and Q. And that's it. Then once this double for loop terminates, we just return the best pair. So one possible execution of closest split pair is that it never finds a pair of points P and Q with distance less than delta. In that case, this is going to return null, and then in the outer call, in the closest pair, obviously you interpret a null pair of points to having infinite distance. So if you call closest split pair and it doesn't return any points, then the interpretation is that there's no interesting split pair of points, and you just return the better of the results of the 2 recursive calls, P1, Q1, or P2, Q2. Now, as far as the running time of this subroutine, what happens here? Well, we do constant work, just initializing the variables. Then notice that the number of points in SY, well, in the worst case, you have all of the points of P, so there's going to be at most n points. And so you do a linear number of iterations in the outer for loop. But here's the key point. In the inner for loop, right, normally double for loops give rise to quadratic running time, but in this inner for loop, we only look at a constant number of other positions. We only look at 7 other positions. And for each of those 7 positions, we only do a constant number of work. Right, we just compare a distance and make a couple other comparisons and reset some variables. So for each of the linear number of outer iterations, we do a constant amount of work, so that gives us a running time of O of n for this part of the algorithm. So as I promised, analyzing the running time of this closest split pair subroutine was not challenging. We just, in a straightforward way, looked at all the operations. And again, because in the key linear scan we only do constant work per index, the overall running time is big O of n, just as we wanted. So this does mean that our overall recursive algorithm will have running time O of n log n. What is totally non-obvious, and perhaps even unbelievable, is that this subroutine satisfies the correctness requirements that we wanted. And remember what we needed? We needed that whenever we're in the unlucky case, whenever in fact the closest pair of points in the whole point set is split, this subroutine better find it. So, but it does, and that's made precise in the following correctness claim. So let me phrase the claim in terms of an arbitrary split pair which has distance less than delta, not necessarily the closest such pair. So suppose there exists a point on the left side and a point on the right side, so that is a split pair. And suppose the distance of this pair is less than q. Now there may or may not be such a pair of points pq. Don't forget what this parameter delta means. What delta is, by definition, is the minimum of d of p1 q1, where p1 q1 is the closest pair of points that lie entirely in the left half of the point set q, and d of p2 q2, where similarly p2 q2 is the closest pair of points that lies entirely on the right inside of R. So If there's a split pair with distance less than delta, this is exactly the unlucky case of the algorithm. This is exactly where neither recursive call successfully identifies the closest pair of points. Instead, that closest pair is a split pair. On the other hand, if we are in the lucky case, then there will not be any split pairs with distance less than delta, because the closest pair lies either all on the left or all on the right, and it's not split. But remember, so we're interested in the case where there is a split pair that has distance less than delta, where there is a split pair that is the closest pair. So the claim has two parts. The first part, part A, says the following. It says that if there's a split pair P and Q of this type, then P and Q are members of SY. Now let me just sort of redraw the cartoon. So remember what SY is. SY is that vertical strip. And again, the way we got that is we drew a line through a median x coordinate, and then we fattened it by delta on either side, and then we focused only on points that lie in the vertical strip. Now notice our counts split pair subroutine, if it ever returns a pair of points, it's going to return a pair of points PQ that belong to SY. First it filters down to SY, then it does a linear search through SY. So if we want to believe that our subroutine identifies best split pairs of points, then in particular such split pairs of points better show up in SY. They better survive the filtering step. So that's precisely what part A of the claim is. Here's part B of the claim, and this is the more remarkable part of the claim, which is that P and Q are almost next to each other in this sorted array SY. So they're not necessarily adjacent, but they're very close. They're within 7 positions away from each other. So this is really the remarkable part of the algorithm. This is really what's surprising and what makes the whole algorithm work. So just to make sure that we're all clear on everything, let's show that if we prove this claim, then we're done. Then we have a correct, fast implementation of a closest pair algorithm. I certainly owe you the proof of the claim. That's what the next video is going to be all about. But let's show that if the claim is true, then we're home free. So if this claim is true, then so is the following corollary, which I'll call corollary 1. So corollary 1 says, if we're in the unlucky case that we discussed earlier, if we're in the case where the closest point in the whole point set P does not lie both on the left, does not lie both on the right, but rather has one point on the left and one on the right, that is, it's a split pair, then in fact the count split pair subroutine will correctly identify the closest split pair, and therefore the closest pair overall. Why is this true? Well, what does count split pair do? Okay, so it has this double for loop, and it thereby explicitly examines a bunch of pairs of points, and it remembers the closest pair of all of the pairs of points that it examines. What does this, so what are the criteria that are necessary for a count split pair to examine a pair of points? Well, first of all, the points P and Q both have to survive the filtering step and make it into the array SY, right? So count split pair only searches over the array SY. Secondly, it only searches over pairs of points that are almost adjacent in SY, that are only 7 positions apart. But amongst pairs of points that satisfy those two criteria, count split pair will certainly compute the closest such pair, right? It just explicitly remembers the best of them. Now, what's the content of the claim? Well, the claim is guaranteeing that every potentially interesting split pair of points, namely every split pair of points with distance less than delta, meets both of the criteria which are necessary to be examined by the count split pair subroutine. So first of all, and this is the content of part A, if you have an interesting split pair of points with distance less than delta, then they'll both survive the filtering step. They'll both make it into the array SY. Part A says that. Part B says they're almost adjacent in SY. So if you have an interesting split pair of points, meaning it has distance less than delta, then they will in fact be at most 7 positions apart. Therefore, count split pair will examine all such split pairs, all split pairs with distance less than delta, and just by construction it will compute the closest pair of all of them. So again, in the unlucky case where the best pair of points is a split pair, then this claim guarantees that the count split pair will compute the closest pair of points. Therefore, having handled correctness, we can just combine that with our earlier observations about running time, and corollary 2 just says, if we can prove the claim, then we have everything we wanted. We have a correct O of n log n implementation for the closest pair points. So with further work and a lot more ingenuity, we've replicated the guarantee that we got just by sorting for the one-dimensional case. Now again, these corollaries hold only if the claim is in fact true. And I've given you no justification for this claim, and indeed even the statement of the claim I think is a little bit shocking. So if I were you, I would demand an explanation for why this claim is true, and that's what I'm going to give you in the next video. All right, so the plan for this video is to prove the correctness of the divide and conquer closest pair algorithm that we discussed in the previous video. So just to refresh your memory, how does the outer algorithm work? Well, we're given endpoints in the plane. We begin by sorting them, first by x coordinate and then by y coordinate. That takes n log n time. Then we enter the main recursive divide and conquer part of the algorithm. So what do? We divide the point set into the left half and into the right half, capital Q and capital R. Then we conquer. We recursively compute the closest pair in the left half of the point set Q. We recursively compute the closest pair in the right half of the point set R. There's a lucky case where the closest pair in the entire point set lies either all on the left or all on the right. In that case, the closest pair is handed to us on a silver platter by one of the two recursive calls. But there remains the unlucky case where the closest pair is actually split with 1 point on the left and 1 point on the right. So to get our n log n running time bound, analogous to merge sort and our inversion counting, we need to have a linear time implementation of a subroutine which computes the closest pair of points, which is split, one on the left or one on the right. Well, actually, we don't need to do quite that. We need to do something only a little bit weaker. We need a linear time algorithm which, whenever the closest pair in the whole point set is in fact split, then computes that split pair in linear time. So let me now remind you how that subroutine works. So it has two basic steps. So first there's a filtering step. So it looks at, first of all, a vertical strip roughly down the middle of the point set, and it looks at only at points which fall into that vertical strip. That was a subset of the points that we called S sub y, because we keep track of them sorted by y coordinate. And then we do essentially a linear scan through sy. So we go through the points one at a time, and then for each point we look at only the almost adjacent points. So for each index I, we look only at j's that are between 1 and 7 positions further to the right than I. So among all such points, we compare them, we look at their distances, we remember the best such pair of points, and then that's what we return from the count split pair subroutine. So we've already argued in the previous video that the overall running time of the algorithm is n log n, and what remains is to prove correctness. And we also argued in the previous video that correctness boils down to the following correctness claim, in the sense that if we can prove this claim, then the entire algorithm is correct. So this is what remains. Our residual work is to provide a proof of the correctness claim. What does it say? It says consider any split pair, that is 1 point P from the left side Q, capital Q, and another point little q drawn from the right side of the point set, capital R, and further suppose that it's an interesting split pair, meaning that the distance between them is at most delta. Here delta is, recall, the parameter passed to the count split pair subroutine, which is the smallest distance between a pair of points which is all on the left or all on the right, and this is the only case we're interested in. There's two claims. First of all, for P and Q, both members of the split pair, survive the filtering step. They make it into the sorted list S sub y, and second of all, they will be considered by that double for loop, in the sense that the positions of P and Q in this array S sub y differ by at most 7. So that's the story so far. Let's move on to the proof. So let's start with part A, which is the easy part, relatively, of the claim. So remember what we start with. Our assumptions, we have a point P. Let's write it out in terms of the x-coordinates, x1 and y1, which is from the left half of the point set. And we have a point Q, which we'll call x2, y2, which comes from the right half of the point set. And furthermore, we're assuming that these points are close to each other. And we're going to use that hypothesis over and over again. So the Euclidean distance between P and Q is no more than this parameter delta. So first, something very simple, which is that if you have 2 points which are close in Euclidean distance, then both of their coordinates have to be close to each other. Right? If you have 2 points and they differ by a lot in one coordinate, then the Euclidean distance is going to be pretty big as well. So specifically, by our hypothesis that P and Q have Euclidean distance less than delta, it must be that the difference between their coordinates in absolute value is no more than delta, and as well, the difference between their y coordinates is at most delta. Okay, and this is easy to see if you just return to the definition of Euclidean distance that we reviewed at the beginning of the discussion of closest point. Okay, so if your distance is at most delta, then in each coordinate you differ by at most delta as well. Now, what does A say? So proof of A. So what does part A of the claim assert? It asserts that P and Q are both members of SY, are both members of that vertical strip. So another way of saying that is that the x-coordinates of P and Q, that is the numbers x1 and x2, both are within delta of x bar. Remember, x bar was in some sense the median x-coordinate, so the x-coordinate of the n/2th leftmost point. So we're going to do a proof by picture. So forget about y-coordinates, that's sort of irrelevant right now, and just focus on the x-coordinates of all of these points. So on the one hand we have x bar, This is the x-coordinate of the n over 2th point from the left, and then there are the x-coordinates which define the left and the right borders of that vertical strip, namely x bar minus delta and x bar plus delta. And then somewhere in here are x1 and y1, the x-coordinates of the points we care about, p and q. So a simple observation, so because p comes from the left half of the point set and x bar is the rightmost x-coordinate of the left half of the point set, the x-coordinate of p is at most x bar. Right? So all points of Q have x-coordinate at most x bar, in particular P does. Similarly, since x bar is the rightmost edge of the left half of the point set, everything in the right half of the point set has x-coordinate at least x bar. So in particular, little q does as well. So what does this mean? So this means x1, wherever it is, has to be to the left of x bar. x2, wherever it is, has to be to the right of x bar. And what we're trying to prove is that they're wedged in between x bar minus delta and x bar plus delta. And the reason why that's true is because their x-coordinates also differ by at most delta. Okay, so what you should imagine is you can imagine x1 and x2 are sort of people tied by a rope at the waist, and this rope has length delta. So wherever x1 and x2 move, they're at most delta apart. Furthermore, x1, we just observed, can't move any farther to the right than x bar. So even if x1 moves as far to the right as it can, all the way to x bar, x2, since it's at most delta away, tied by the waist, can't extend beyond x bar plus delta. By the same reasoning, x2 can't move any further to the left than x bar. x1 being tied to the waist to x2 can never drift further to the left than x bar minus delta. So that's the proof that x1 and x2 both lie within this region that defines the vertical strip. So that's part A. You have any split pair whose distance between them is less than delta, they both have to wind up in this vertical strip, and therefore wind up in the filtered set, the pruned set, S sub y. So that's part A of the claim. Let's now move to part B. Recall what part B asserts. It says that the points P and Q, the split pair that are distance only delta apart, not only do they wind up in this sort of filtered set SY, but in fact they're almost adjacent in SY, in the sense that the indices in the array differ by at most 7 positions. And this is the part of the claim that's a little bit shocking. Really what this says is that we're getting away with more or less a variant of our one-dimensional algorithm. Remember when we wanted to find the closest pair of points on the line, all we had to do was sort them by their single coordinate and then look at consecutive pairs and return the best of those consecutive pairs. Here what we're saying is really once we do a suitable filtering and focus on points in this vertical strip, then we just go through the points according to their y-coordinate. And okay, we don't just look at adjacent pairs, we look at pairs within 7 positions, but still we basically do a linear sweep through the points in SY according to their y-coordinate, and that's sufficient to identify the closest split pair. So why on earth would this be true? So our workhorse in this argument will be a picture which I'm going to draw next. So I'm going to draw 8 boxes which have height and width delta over 2. So here delta is the same parameter that's passed to the closest split pair subroutine, and it's also the same delta which we're assuming P and Q are closer to each other than. Right? So remember that's one of our hypotheses in this claim. The distance between P and Q is strictly less than delta. So we're going to draw 8 delta over 2 boxes, and they're going to be centered at x bar, so this same center of the vertical strip that defines SY, and the bottom is going to be the smaller of the y-coordinates of the points P and Q. So it might be P, it might be Q, it doesn't really matter. But so just the bottom is going to be the smaller of the two. So the picture then looks as follows. So the center of these collections of 8 boxes is x bar, the bottom is the minimum of y1, y2. We're going to have 2 rows and 4 columns. And needless to say, we're drawing this picture just for the sake of this correctness proof. Right? This picture is just a thought experiment in our head. We're just trying to understand why the algorithm works. The algorithm, of course, does not draw these boxes. The subroutine, the closest split pair subroutine, is just that pseudocode we saw in the previous video. This is just to reason about the behavior of that subroutine. Now, looking ahead, I'll make this precise in 2 lemmas that are about to come up. What's going to be true is the following. So either P or Q is on this bottom line, right? So we define the bottom to be the lower y-coordinate of the 2. So maybe, for example, Q is the one that has the smaller y-coordinate, in which case it's going to be somewhere, say, down here. P, remember, is from the left half of the point set, so P is maybe going to be here or something. And we're going to argue that both P and Q have to be in these boxes. Moreover, we're going to argue that these boxes are sparsely populated. Every one contains either 0 or 1 point of the array S sub y. So what we're going to see is that there's at most 8 points in this picture, 2 of which are P and Q, and therefore if you look at these points sorted by y-coordinate, it has to be that they're within 7 of each other. The difference of indices is no more than 7. So we're going to make those 2 statements precise one at a time via the following 2 lemmas. Let's start with lemma 1. Lemma 1 is the easy one, and it states that all of the points of S sub y, which show up in between the y-coordinates of the points we care about, P and Q, have to appear in this picture. They have to lie in one of these 8 boxes. So we're going to argue this in 2 steps. First, we're going to argue that all such points have to have y-coordinates within the relevant range of this picture between the minimum of y1 and y2 and delta more than that. And secondly, that they have to have x-coordinates in the range of this picture, namely between x bar minus delta and x bar plus delta. So let's start with y-coordinates. So again, remember this key hypothesis we have. Okay, we're dealing with a split pair PQ that are close to each other. The distance between x and y is strictly less than delta. So the very first thing we did at the beginning of this proof is we said, well, if their Euclidean distance is less than delta, then they have to differ by at most delta in both of their coordinates, and in particular in their y-coordinate. Now remember, whichever is the lower of P and Q, whichever one has a smaller y-coordinate, is precisely at the bottom of this diagram. So for example, if Q is the one with a smaller y-coordinate, it might be on the black line right here. So that means in particular, x has y-coordinate no more than the top part of this diagram, no more than delta bigger than Q, and of course all points with y-coordinates in between them are equally well wedged into this picture. So that's why all points of SY with y-coordinate between those of P and Q have to be in the range of this picture, between the minimum of the 2 y-coordinates and delta more than that. Now what about horizontally? What about the x-coordinates? Well, this just follows from the definition of S sub y. So remember, S sub y are the points that fall into this vertical strip. How did we define the vertical strip? Well, it had center x bar, and then we fattened it by delta on both sides. So just by definition, if you're in SY, you got to have x coordinates in the range of this picture. X delta plus minus, x bar plus minus delta. So that completes the proof of the lemma. So this is just a lemma, so I'll use a lowercase QED. Remember, this is just a step toward proving the overall correctness claim. But this is a good step. And again, the way to think about this is it says we draw these boxes. We know either P or Q is at the bottom. The other one is going to be on the other side of the black line x bar, but will be in some other box. So perhaps maybe P is here. And the lemma is saying that all the relevant points of SY have to be somewhere in this picture. Now remember, in our double for loop, we only search 7 positions away. So the concern is that this is a sort of super highly populated collection of 8 boxes. That's the concern, but that's not going to be the case. And that's exactly what lemma 2 is going to say. Not only do the points between P and Q and y coordinates show up in this diagram, but there have to be very few. In particular, every box has to be sparse with population either 0 or 1. So let's move on to lemma 2. So formally the claim is we have at most 1 point of the point set in each of these 8 boxes. And this is finally where we use, in a real way, the definition of delta. This is where we finally get the payoff from our realization long ago that when defining the closest split pair subroutine, we only really need to be correct in the unlucky case, in the case we're not handed the right answer by one of our recursive calls. We're finally going to use that fact in a fundamental way. So we're going to proceed by contradiction. So we're going to think about what happens if there are 2 points in a single box, and from that we'll be able to derive a contradiction. So call the points that wind up in the same box A and B. So to the contrary, suppose A and B lie in the same box. So maybe this is A here and this is B here, at antipical corners of this particular box. So from this supposition, we have 2 consequences. First of all, I claim that A and B lie on the same side of the point set. They're either both in the left side Q or they're both in the right side R. So why is this true? Well, it's because every box lies either entirely in the left half of the point set or in the right half of the point set. Recall how we define x bar. X bar is the x-coordinate of the rightmost point amongst the left half of the point set, capital Q. So therefore, points with x-coordinate at most x bar have to lie inside the left half Q. points with x coordinates at least x bar have to lie inside the right half of the point set, capital R. So that would be like in this example, A and B both lie in a box which is to the right of x bar, so they both have to come from the right half of the point set, capital R. This is one place we're using that there's no ties in x coordinate, so if there's a point with x coordinate x bar, we can count it as part of the left half. So every box, by virtue of being either to the left of x bar or to the right of x bar, can only contain points from a common half of the point set. So that's the first consequence of assuming that you have 2 points in the same box. The second consequence is, because the boxes are small, the points got to be close. So if A and B cohabitate a box, how far could they be from each other? Well, the farthest they could be is like I've drawn in the picture with the points A and B, where they're at opposite corners of a common box, and then you bust out Pythagorean's theorem, and what do you get? You get that the distance between them is delta over 2, the side of the box, times root 2. And what's relevant for us is this is strictly less than delta. Okay? But now, here's where we use, finally, the definition of delta. Consequences 1 and 2 in tandem contradict how we define delta. Remember what delta is? It's as close as a pair of points can get if they both lie on the left side of the point set or if they both lie on the right side of the point set. That is how we defined it. As small as a pair of points on a common half can get to each other. But what have we just done? We've exhibited a pair A and B that lie on the same half of the point set and are strictly closer than delta. So that contradicts the definition of delta. So that completes the proof of lemma 2. Let me just make sure we're all clear on why, having proved lemma 1 and lemma 2, we're done with the proof of part B of the claim, and therefore the entire claim, because we already proved part 1 now a long time ago. So let's interpret the two lemmas in the context of our picture that we've had all throughout in terms of the 8 boxes of side length delta over 2 by delta over 2. So again, whichever is the lower of P and Q, and again, let's just, for the sake of concreteness, say it's Q, is at the bottom of the picture. The other point is on the other half of the line x bar and is in one of the other boxes. So for example, maybe P is right here. So lemma 1 says that every relevant point, every point that survives the filtering and makes it into SY by virtue of being in the vertical strip, has to be in one of these boxes, okay, if it has Y coordinate in between P and Q. Lemma 2 says that you can only have 1 point in each of these boxes from the point set. So that's going to be at most 8 total. So combining them, lemmas 1 and 2 imply that there are at most 8 points in this picture. And that includes P and Q, because they also occupy 2 of the 8 boxes. So in the worst case, if this is as densely populated as could possibly be, given lemmas 1 and 2, every other box might have a point, and perhaps every one of those points has Y coordinate between P and Q. But this is as bad as it gets. Any point of the strip with Y coordinate between P and Q occupies a box, so at most there are these 6 wedged in between them. What does this mean? This means if from Q you look 7 positions ahead in the array, you are guaranteed to find this point P. So a split pair with distance less than delta is guaranteed to be identified by our double for loop. Looking 7 positions ahead in the sorted array SY is sufficient to identify, to look at every conceivably interesting split pair. So that completes the assertion B of the correctness claim, and we're done. That establishes that this supremely clever divide and conquer algorithm is indeed a correct O of n log n algorithm that computes the closest pair of a set of n points in the plane.